This case study is a case study of an apartment building in HOOGEZAND, Groningen, the Netherlands. It's located in the northern part of the Netherlands, near the city of Groningen. It's actually part of a research project financed by the Ministry of Economic Affairs in the Netherlands. It's called the optic GBES project. And the goal of this project was to check heat transfer calculations in the ground to see if the principal mathematics and physics are correct, and also to see what happens with interference, thermal interactions between systems, and to see if we can improve the efficiency, operational efficiency of the systems. It's a commercial project, 45 apartments with individual heat pumps and individual borehole heat exchangers. A number of partners in this project were Nathan, which is the drilling company and also the installer of the heat pump systems, and the manufacturer of the heat pump systems, Deltares, which is the Dutch Geological Institute, SIKB, which is the Dutch Institute for the Protocols about Ground Source Energy Systems, and KWR, a Dutch Water Cycle Research Institute. The system itself, the project itself, it's a monitoring project to assess design and thermal interference calculations and optimize operational heat pump performance. And different steps were taken. First of all, we had a very detailed site characterization, including geophysical logging of boreholes and thermal response testing of 3 boreholes. We even had declination measurements, so measuring how vertical the boreholes are drilled. We then selected a number of apartments for the monitoring. 3 apartments were monitored in detail, both the apartments themselves, but also the boreholes connected to those apartments with distributed temperature sensing using fiber optic cables installed across the whole length of the borehole. And we had additional boreholes drilled at small distances from the borehole heat exchangers to measure the temperature evolution in the ground at different distances from the actual borehole heat exchangers. Here we see some results of the geology and the thermal response testing and the declination measurements. The geology are mainly sandy deposits, so we would assume a fairly homogeneous soil profile. If we look at the picture of the deviation of the vertical on the right, we can see that there are really significant deviations with depth of the vertical, which is important because in the protocol we also say things about what is the minimum spacing between boreholes to prevent one borehole from hitting another one. And actually on these declination measurements, supported the rules that we have in the protocol at the moment for minimum spacing between boreholes as a function of borehole depth. Also, we did a thermal response test on all 3 boreholes that we are going to monitor. And what we can see in a little table is for the thermal conductivity, the original design value was 2. If we base a calculation on detailed geological data, we get a thermal conductivity of 2.24. But if we do the actual measurements with the thermal response test, we find 3.3. Very much higher. This is an indication of, let's say, limitations of the available data, because in this case in Groningen, the sands are actually quite overcompacted due to cover in the previous, previous ice age. And that causes better contact between the sand particles and therefore a higher thermal conductivity not found in other parts of the Netherlands. Okay, so here we see a more detailed layout of the whole borehole field with in the call out the actual boreholes that we're going to monitor and the observation points around them. So the red circles are the boreholes that we're going to monitor. The blue circle is another borehole that's not going to be monitored, and the triangles are the observation wells where there is no borehole heat exchanger, but there is a fiber optic cable to measure the temperature. On the heat pump system side, we have 3 energy meters installed. You can see that on the left. 3 energy meters measuring the heat delivered and cool delivered to the apartment, the domestic hot water being used by the apartment, and the heat and cool extracted from the ground. We also have an electrical kilowatt-hour meter in the heat pump to measure the electrical consumption of the compressor and the electrical consumption of the borehole pump. On the top, you can see a little box with 2 gables going in. On the right, you can see this box opened up, and here you can see an Ixon VPN router that we used for the external connection, and a little data logger that Groen Holland developed based on a system on a chip, an actual BeagleBone little low-cost computer with a Modbus interface to read out all the energy meters and also read out the heat pump data. Here, a result of the monitoring data of all apartments. What was really interesting to see is that almost all apartments have a heating demand and energy in megawatt hours per year, a heating energy used for space heating that is lower, and in a number of cases significantly lower than the design value, which is the red line. At the same time, there are a number of apartments, 1, 2, and 3, that have a higher than design heating load in the same period. So this is actually quite interesting, and we looked at different explanations, like is it correlated with the floor number, like the top floor could have a higher heating demand due to the fact that you have heat loss through the roof, or a northern or western or eastern exposition, which gives a better solar irradiation on the east or on the west, in the east in the morning and in the west in the afternoon. So we could not find any correlation with these type of parameters.